तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been looking at design applications in the previous classes, and some of which are PCI orbiter, and therein we have seen also an example of video compression system and how to configure them based on PCI bus. And for that we needed a controller, and that is what we had developed on that occasion. And subsequently we have gone for another application called a traffic controller, and we have also seen video compression algorithm, how to develop the algorithm, and then finally code it in Verilog so as to make a encoder, video encoder as such. And we have used basically the discrete cosine transform and quantization in order to effect the compression, and thereafter we need to gain experience on actual hardware, and for that we need to have FPGA boards. And so far what we have seen is only the CAD tools, namely the model sim tool to do the simulation, namely to get the timing diagram and so and analyze the circuit based on that study. And thereafter we also use the simplified tool in order to do the logic synthesis. It mapped not only the device but also the you got RTL view, etc. In that synthesis tool, and it also generates an EDF file which we had taken for Xilinx place and route, and mapped the actual device and done place and route. And we have also seen the back annotation so as to reflect the actual gate delays and then plow it back into the model simulator so that we could see the actual gate delays incorporated. And place and route reported, frequency of operation reported by the place and route is what is to be actually taken into account when we actually design the system. And once we run it through place and route say here in this case Xilinx place and route, which we have already seen, then the frequency of operation reported by that is more or less going to be operating on the right on the FPGA board, and which we are going to see presently, and this is what is going to be done in the next few lectures. And prior to this, we need to become familiar with some of these boards. First, let us see, there are many vendors as far as the boards are concerned, and namely Xs and Avnet, and even Xilinx has some boards available, and plenty of other manufacturers are also available for manufacturing for making FPGA based boards, and they have very many features which you can readily use in many of the applications that you need for your own development. And let us first have a look at Xs board, and this is from Xs Corporation, and you can that's a site www.xs, this is the spelling, note this, xews.com. So if you go into that, you can download all the manuals, etc., and when you purchase these boards, you will also get a copy of that on CD fundamentally, along with the software that goes along with this. And this is what is called XSB board, and what we have here is version 1.1, and this has XCV 800 as the device, which we will be seeing shortly. And prior to that, this is basically the manual of this Xs Corporation user manual for the board, and let us go to the relevant point, and so that we can see what board contains. These are all the features of this Xs board, and this contains programmable logic chips, and there are basically two chips available. One is for your own application, wherein you have to download the bit stream which you have got in place and route, and this is the place where you have to download your bit stream, and that is based on Xilinx Vertex FPGA, and the device is XCV 800. On many occasions, I think we have used some such device in our design while doing earlier, and it is a 240 pin PQFP package, and this is what is housed on the board. We will be seeing the board both pictorially as well as the actual hardware, and we will also see the whole thing configured for one of the applications, and we may be looking into the applications, some of the applications which we have designed or going to design. And this particular FPGA, in fact, this socketed, and I'm sorry, this is not socketed, and some of the FPGA boards are socketed, and this present board I don't think it's socketed, which you can have a look later on. And it can otherwise we may have to, if you want to change it to different FPGAs of different capacities. For example, XCB 50 is for 50,000 gates capacity, and like that they have very many FPGAs available, either on, it has got to be a different cards as such. And what we have here and we are going to demonstrate will be based on this XCV 800. This is at the highest end of their product here for the time being, and when new devices come, they may have incorporate that and bring about a different board for that as well. And this is capacity 800 stands for 800,000. Actually, it goes for 88 kilo gates here, and this is on this XSV board, and this is the main FPGA which in which we will be downloading our application programs. For example, if you want to put a traffic controller, which we have designed before, and we need to download that bit stream onto this FPGA here. And next is there is also another FPGA equivalent. This is called complex programmable logic device, abbreviated as CPLD, and this will not contain as many gates as XCV 800. It may go only for few thousand gates here, and this CPLD is used to manage the configuration of the Vertex FPGA. That's the Vertex FPGA is what we are having here. it is the one which will take in the bit stream for your application, and whatever application you are downloading, it will be on this FPGA, and this circuit is configured on this FPGA. And you also need, in order to do the management, you need this CPLD as well, and that is it manages the configuration of the Vertex FPGA via the parallel port. There is also on the board a parallel port, and which can be connected to the parallel port of the standard computers, say personal computers such as Pentium, and LPT1 or LPT2. There is a provision for selecting any of this that you want, and it also has a serial port, and through which RS-232 type of communication can be undertaken here, and for any of your application you can use this, or you can even download the bit stream through the serial port, but it is going to be a time consuming thing. It is preferable that we take the parallel port, and this is what we are going to adopt. And it also has flash RAM. Flash RAM is a non-volatile RAM. Even with the power switched off, it will still retain whatever its contents are, and so it is a convenient media wherein you can put your bit stream. So that is the application circuit that you have configured can be put into the flash RAM, and even with the power off, and the code is not disturbed, the bit stream is not disturbed. So when you switch on power once again, it can immediately start working on your code, or rather the circuit which you have configured. The CPLD also controls the configuration of Ethernet chip, and you have a Ethernet chip also available right on the card, and it is also capable of having different clock speeds for FPGA operation, and it goes right up to 100 megahertz, and lower values also you can have. This we will see shortly, and what different ranges, how to program that, all that we will be seeing. And it also has 16 megabit of flash RAM. The flash RAM we have already seen here, and that can store multiple configurations. That means different bit streams can be stored at different location and retrieved at any point of time for operation, or it can have general purpose data, which may be for example you may be working on video compression, so for which you may require huge storage. So you can use this flash RAM, so that since it is non-volatile, it will be very handy to use in flash RAM as such. And it also has two independent 512K into 16 static RAM banks. It is basically organized as 8 bits, that is a byte oriented thing, and in fact two chips are there here in order to give you 1 megabyte of storage here. Like this you have two sets, so in total you get 2 megabytes of storage RAM, which is connected to the IO pins of the FPGA, and that FPGA is basically on Xilinx FPGA, and part of it could be on CPLD or wholly CPLD, which we will be seeing when we see the actual pin configuration. Next we have very good features. For example, a video decoder is available in order to cater to NTSC, PAL, CCOM signals. So this is the TB signal that you will be getting, and you can collect this one and convert that analog signal into digital signal. So this is what we refer as digitization, and it is through RCA jack or S video connector, and it outputs this there is a video decoder chip on the board, and that brings about this digitization, and it outputs naturally to the FPGA for further processing, such as video compression we have seen earlier. And that being involved, we may not cover this on the board. We may cover simpler applications such as traffic light controller and so on. And it also has a RAM plus DAC. DAC stands for the digital to analog converter, and this can be used for converting color of for example NTSC you have received. If you want to display it on the monitor, the computer monitor that you have right here, and you can that is called a VGA interface or VGA monitors. You can it can be connected through this RAM DAC chip, and it has some 256 entries available, and that much store is available on this, and you can configure for true color. say 24 bit color map you can configure, and that is used by the FPGA to output video to a VGA monitor. In addition to this, it also has a decoder stereo codec here on the board, and it also does the digitization of the actual audio analog signal. The audio range, although it is only from 20 to 20 hertz to 20 kilohertz, actually this stereo codec is capable of processing right from 0 to 50 kilohertz, and resolution is this, once the digitization is involved, you speak of resolution number of bits, so it can handle up to 20 bits, and we have already seen you have an Ethernet chip for connecting it to a LAN, and up to 100 Mbps link is possible with this board, and you also have some expansion headers which we will be using for some of the applications that we are going to consider, and 2 expansion headers are available right on the board, and they are all basically connected to the FPGA IO pins, and total number of such IOs are 76, putting together all the both the expansion headers, and right on the card you also have some 4 push buttons which you can configure for any of your application, and one 8-bit DAP switch is also available, and it provides general purpose inputs to FPGA as well as the CPLD. In addition to this, you have 2 7-segment LEDs and one bar graph LED, and I think it is 10 bar you can display, and it lets the FPGA as well as CPLD display status information. You can display the any information that you want here, or any parameter engineering units that you are processing in your application can also be displayed by using some of these displays. It also has a mouse keyboard interconnection through a port called PS2, and this once again is connected to the FPGAs, and it offers the FPGA access to common PC input devices, and you have a USB port, and here it is capable of, it is basically a serial link, and it is connected to once again FPGA through a special chip right on the chip, and it has a bandwidth of 1.5 Mbps to 12 Mbps. This is the rate at which you can communicate serially, and you also have a parallel as well as serial ports available right on this, and we will be using parallel port in order to download the bit stream that we have for our application, and it will parallel serial port interfaces let the CPLD send and receive data in a parallel or serial format similar to a PC. This is precisely same as a PC LPT printer interface, which is a parallel port which you are already familiar, and it also has another way of communicating the bit stream in addition to this parallel or serial fashion, and that is by a special cable called exchequer cable. Of course, we will not be using this here, and this also helps in downloading your bit stream, and you can also read back what you have already configured on the FPGA, and the board will have to be connected to a power supply, external power supply. You can connect either a 9 volts power jack or a specially connected ATX power connector, and right on the board. Both of them are on the board, and it lets the XSP board receive power from a standard ATX power supply. This is their supply, which we do not have, and in lieu of this we have just a simple power supply, 9 volt supply, or you can use if you have an adapter for this you can use, but current rating will have to be 1.5 amps at least. So that is what you have to take into account, and normally the board demands 5 volts and 3.3 volts, perhaps at 2.5 volts also DC is also required, and all are derived right from 9 volts which we can supply externally, or you can supply from this power supply, ATX power supply, and so we can now having seen all these features of the board, we can see this pictorially how the board looks like. This is how the board looks. You can see right on the top there is a this is a jack here, and you can connect the conventional 9 volts jack and supply power, and power requirement is you have to have at least 1.5 amps, and we also need the parallel port interconnection. That is associated with this will be a cable parallel port cable will be there, and this will go into the LPT1 or LPT2, which you can configure on the host processor, namely the Pentium. So it is through this cable that you are going to download into the Vertex FPGA, which is here, and before we arrive at this, we will see different all other features in the same order. So in addition to this parallel port, we also have a serial port, and you can use for any of the application. For example, you want to have RS-232 type of serial link for between your board and the PC personal computer, and you can have a serial cable connected, and whatever application you have configured, you can download your data information through the serial port onto the host system, and vice versa, and thereby you can configure a total system for catering to a particular application. Say for example, if you want to do a data acquisition system, so you can have you can send any data based on real time, and you can send to and fro data between this FPGA board and also the personal computer. So for that you can use the serial port, and as we have already seen that one RCA jack and S video jack are available here, and there is also a chip which is the video decoder, and this takes in the NTSC or PAL SECOM TV signal and routes that particular to the Vertex FPGA pins. Via the pins, I mean IO pins, you can transact whatever image that you have collected via this signal, I mean be it NTSC or PAL signal, you can route it to the FPGA and do further processing such as compression. And next we have also a power supply connector here, and that is what needs to be connected here. Either you connect this or the 9 volts here. So we are going to use only the 9 volts connection, not this. And we have also seen an exchequer interconnection is also there through this, and we are not going to use. Instead of this, we are going to use the parallel interface in order to connect it to a PC LPT1, and we have another switches here. For example, an 8-bit DAP switch is available here, and you can use it for any of your application. For example, you want to set a particular value, a timing value. Suppose you are running a timer, you can set your timer or etc. right at the DAP switch, and or any other parameter you wish to set, you can set through the DAP switch. And this will be connected to both the CPLD, which is housed here, and as well as the Vertex FPGA here. And what we have is on board XCB 800 is capable of nearly 900,000 gates. We can put a huge circuitry inside this. Our application is going to reside here. It is going to come through this parallel port right onto this FPGA, and we are going to download a dot bit. For example, if it is a traffic controller, we are going to generate a traffic controller dot bit by using place and route, and that particular bit stream we are going to download and onto this. For this, you need a software associated with this board. XS also supplies software which we need to load it on to the system, and that will have to be run, and only then you can communicate with this board effectively. In fact, without that it will be it's almost impossible to communicate with this. Right? You have to have that. And in addition to this CPLD, we also have 2 digits 77 LEDs, which we have already seen, and this we will see little later some of details how you go about connecting different segments. In addition to this, we mentioned that there is a 10 bar segment, that is what is here. In fact, similar segments will be placed here, one segment here, one below another, all 10 will be available here. This is a bar display, and you can use it for some display of histograms in some of your engineering units you may design, and you can use for such application. And so also the two LEDs, and you also have a 16 megabit flash RAM available, and that is housed here. And in addition to this, we have 2 megabytes of static RAM storage, and as I mentioned, they are all arranged as 512K bytes here, and two such devices would give you 512K into 16, which we have already seen in the features earlier. And like this, we have two sets here. So in totality, you get 2 million bytes of RAM storage, and you have further this expansion connector. And basically, suppose you are not satisfied with the storage available on this 2 million bytes storage, you can expand it by using this expansion connector, and or you may have to disable, while expanding you may have to disable this RAM if you want to put much more storage, or you do not want to use the internal storage. So you may have to put an extra card outside and connect that card to this expansion connectors here available on both sides, and while doing so you may have to disable this by appropriate jumper connection, which is available on the board, and all these details are available in the manual, which part of which you are already having a look right now. And what we are going to do is, we are not going to put an external RAM, we are not even going to use the internal RAM, and for one of the applications to start with, we will be going for a traffic light controller, which we have already seen, which you are already familiar. That will be the first application we will be taking, and for that particular application we need this expansion connector, and we do not need any other resources we have already seen except for the power supply and the parallel port connection. And we also have, in addition to this, we will we will see more details of expansion connector later on. And we have also seen there are 4 push button switches, and they are all placed here in this order. SW1, 2, 3, 4 are placed in this order, and we have an Ethernet chip here available, and we have also seen that a RAM DAC used for VDU VGA monitor connection, it is here. VGA output is available through this connector, and the processing chip is this available here, and we also have a port for mouse keyboard connection, and a USB port is available here, and for all these different chips are also used in here, one of this here, and we also have a stereo input. You can give the audio input here, and whatever so for example you want to compress the audio, you can route this particular thing. It will have a chip, it has a chip here which digitizes and gives a 20-bit resolution output, which can be connected to the say FPGA, and you can do the compression of sound. You can do MP3 for audio layer. You can, if you want, you can do such a project based on using this, and for that purpose you can use this. For any other processing of audio signal you can use, and since only digitized signals are available here right onto the FPGA pins, you can do any processing that you wish, and you can have an USB port, which we have already seen, and it is capable of up to 12 Mbps. So you can have establish a serial link in addition to this RS-232 serial link, which we have already seen, and that will go only for say 19,600 baud. Baud means bits per second, and this is the board feature that we have had a look, and we will actually have a look at the board when after a while. And before this, there are the manual gives lots of jumper settings, etc., which you will have to go through yourself, and there is also a software associated with that, which you will have to install, as I mentioned before, and we will skip this because it is a matter of details pertaining to how to configure. So now what is important is we have already seen how to apply power. There is a jack there, and there are two ways of applying power. Either you go for 9 volts, which we are going to do, and through a jack, separate jack, or ATX power supply supplied by them, XS corporation, and for which you need to connect to a different connector, place, and I noticed that 1.5 amps is the actual requirement. So, in real practice it is taking less than 1 amp, but when you configure the clock, etc., it will require, it may touch 1.25 amps or so. So, if you put 1 amp supply, you will get into trouble, it will start malfunctioning. So, be on your guard while selecting the power supply, and see the ensure that it is capable of supplying at least 1.5 amps. And when supply is supplied, there is also an LED to indicate that the power is on. So, what we are going to do is, we had to follow certain procedure as far as this board is concerned, not to use it for your application. The first thing is, you may have to when you connect the board, and the board connection is quite simple, and to the FPGA board is connected cable to the parallel port and connected straight away to the LPT1 printer or LPT2, any parallel port on your host system can be connected, and in addition to the power supply, that is the only connection that you really require on the board, and we will be seeing this later on. And once you have connected and supplies are on, and of course for the system as well, host system as well, and you have what is called a separate window, and if you for example, this window, what it says is GXS test. If I will first open the this will be very difficult for you to look into the onto the screen, but I can make out what it is. Say if I just say that it is for test, so that is a icon for text. If I double click what I am doing, it opens this window. It may be very difficult for you to view, so therefore I will go back to the same thing, and GX test, this is a bloated up view, and you notice that you can select different boards. For example, if it is XCV 800, so you have to click here. For example, I will go back, that is right here. This is the icon which was clicked earlier, and this is the one which will actually configure the actual system, and which we have already seen. And if you click here, I am going to click here, it will open out a list of boards. So, there is over a dozen boards are available, and for example, XSV 800 is the last thing that is here, then 50, 100, 300, so many other boards are available. And once you have selected the desired one, for example, XSV 800 you have to do, what is shown here is 300, we have to switch, select XSV 800 in the way that I have already shown. And similarly, suppose you have connected to the host some other printer, port connection, for example, instead of LPT1, had you connected LPT2 or LPT3, then you have to once again select by this drop menu here by this, and after this you have to just click on test, then immediately a test sequence will be followed, and I am not going to do this because this is a regular thing which you can very easily do yourself. So, this is what you have to do. You have merely to click on this test, first click on the select the board and select the port, and then click on the test, and then once the test is passed, if it is not passed, it will tell you what the reasons are why it is not passing, and you will be led step by step in order to correct. And if you can't correct through all those steps, you will have to get in touch with the manufacturer, and once you are done with the test, you can exit by closing this button. So, for example, I can exit here, and next is, so I will read out what I have said here in case you find it difficult to read it out yourself. Once your XSV board is installed and the jumpers are in the default configuration, you will be told what jumpers to install, and the sequence etc. will also be told step by step, and failure if any will also be reported, and it will help you to the maximum extent possible. And you can test the board using the GUI based GX test utility as follows. So, you start GX test by clicking on this icon that we have already seen, placed on the desktop during the access tools installation. This during the installation time only you need to do this. Subsequently, for subsequent use you do not need this, and so also the clock, if you are not going to change the clock, which we will be seeing next. And by clicking on this you get this one, which is what we have already seen. Next you select the parallel port that your XSP board is connected to from the port, this also we have seen. Then GXS starts with parallel port LPT1 as the default, but you can also select LPT2 or LPT3 depending upon the configuration of your PC. So this is for different boards which we have already seen. I am not going to read out everything, only the salient points I am going to read. GX test will configure the FPGA to perform a test procedure on your XSP board. This is what the test is for. And after several seconds you will see a 0 displayed on the LED digit if the test completes successfully. If it is not successful, E will be displayed, and a status window will also appear on your PC screen informing you of the success or failure of the test. This is what we have already seen. If your XSP board fails the test, you will be shown a checklist of common causes for failure. If none of these causes applies to your situation, then test the XSP board using another PC, and he gives their experience. Otherwise you have to get in touch with the manufacturer. So we also have next is to program the clock, and you have to do the setting and in order to program the clock. For example, as a default you can run the your FPGA based design right at 100 megahertz, and there will be a divisor which will be seeing shortly. If that that divisor is 1, naturally you will get 100 megahertz as the operating frequency. Suppose you put the divisor 2, you will get 50 megahertz, and so on. You can operate at different frequencies. And so for example, XSP board has a 100 megahertz programmable oscillator, and the chip used for this purpose also is mentioned here, and the master frequency can be divided by factors 1, 2 right up to 2052. So this is what you can put in the menu that is going to come here, and for corresponding to 2052 you will get a 48.7 kilohertz, and this will be the operating frequency of your actual board, and the divided frequency is sent to the rest of the XSP board circuitry as a clock signal. So this is the master clock, we can say, after the division is incorporated. The divisor is stored in non-volatile memory in the oscillator chips, so it will resume operation at its programmed frequency whenever power is applied to the XSP board. You can store a particular divisor into the oscillator chip by using this clock, what we see as the icon here. So you can click on this in order to start. By clicking on this clock icon on the desktop during the access tool installation, this out comes the pops window, which is similar to what we have already seen for the test, with the exception that it is for clock. And once again you have to select your board type here. Here you have to select 800 and LPT1, which is already there here, and here you have to key in 1 or 2 depending upon how many megahertz of operation you want. For example, if you put 2, I think we are going to use divisor 2, is it right? And so that will give corresponding 50 megahertz operation. And so once this is done, you can just say click on set, and then finally you can exit. Suppose you do not want the clock generated in this fashion, you can also feed an external clock by putting this tick. Naturally the external clock will be taken, in which case you have also to install the jumper right on the board, which you can get it from the manual. And we are not going to use this feature, we are going to use this divisor, and we are going to put 2 for our traffic controller application, which we are going to take next. So what we have already described is already here, and I do not have to go in through all this. Next step is for this, you can, the icon is here, so this is clock. So this precisely what we got for the clock, and if I say exit, it will go off, and or you can dismiss it off. And next one is we have to load the bit stream, and what you have already developed during the last right up to the place and route. You have got a bit stream, and that is what you need to download in order to download your application code. So, prior to doing this one, you also need for you have to initialize CPLD, because that particular CPLD is for managing the whole configuration, and it can also you can also put your codes and execute small codes, and major codes will always be residing in the FPGA vertex 2, and this particular menu is once again for board selection. For example, XSV 800 you can select here, and once again the port which we are all seeing along all along, and this is for LPT1 because we have connected LPT1 in this case. And here you will see that one field for FPGA as well as CPLD, and it is here you have to drop the actual bit files, and you have to have ready another window opened for the bit files, the folder in which you have put your bit file, and just pick it up and drop it here. So, then after that this load which is not energized right now, that will get activated, and once you press the load button, it will download the bit stream that is available here. And suppose you want to put from a file into a RAM. So, we have already seen 2 megabytes of RAM is available, or flash RAM is also available, and that can be put here in this. This column is for RAM, and this is for the flash RAM and or E square PROM. And you have once you say RAM or flash RAM, there will be a low order address as well as high order address. This is the it's basically starting from this address to address whatever is available in the file, transfer that particular file contents into this particular RAM whose address starts from here low address and ends up with high address, and you can use that for this. And in order to transfer your bit stream, I mean configure bit stream, you do not require any of these features, and we may not be using this, and we will be using this field. And before that, let me read what it has to say. We had to click on GXS load icon placed on the desktop during the XS tools installation. This brings up the window shown below. Then select the type XSV board you are using and the parallel port to which it is connected as described previously. So, after setting the board type and parallel port, you can download an .svf file to the CPLD on your XSV board simply by dragging it into the FPGA CPLD area of the GXS load window as shown below. To program the CPLD with the parallel port interface, drag the, so this is the file you had to drag in order to program the CPLD. This is a download parallel, am I right in this? This is a download parallel, it is a .svf extension file, and it is there in XTools XSV folder. And so, once you download this one, I mean drop it in this field. So, once again this will, that load will be energized, and then you have to press the load, and I think next described will be that. We also have another menu displayed here, and you can see this. This is what is another window opened. You go to that particular folder, for example, C XS tools for stroke XSV, and you have to download, you have to pick up that download PAR, that is for short form for the parallel, that .svf file. Just click on the mouse, do not release it, and drag it there. You will see that this file is accompanying here, and drop it here when you come into this. Once you drop, that file will be got here, listed here, and this will be energized. The load button will be energized, and then you can press the load, then the actual downloading will take place, taking this as the source file, and CPLD will be programmed. Once you release the left mouse button and drop the file, the highlighted file name appears in the FPGA CPLD area and the load button in the GXS load window is enabled. Clicking on the load button will begin sending the .svf file to the CPLD on the XSV board through the parallel port connection. During the downloading process, GXS load will display the name of the file and the progress of the current download. So, this is what we have already seen, and this is precisely what we have already seen. So, we will skip this, and only difference is this load has been energized here. That is what, once CPLD is programmed with the parallel port interface circuit, you can remove the shunt. These are all jumper settings which you can easily follow. I am just skipping all the jumpers. You might really get bored listening to all jumper settings. So, next is the actual application file. For example, you want to have your traffic light controller. So, we will be having a traffic light controller in your folder, just as we had the previous folder for the CPLD download pair, and here will be listed your traffic controller .bit, and once the CPLD is programmed with the downloading interface circuit, you can download bit streams into the Vertex FPGA using the GXS load. So, utility, make sure that is a shunt across this. Once again a jump, he is reminding that a jumper must be installed, and you had to do lots of jugglery with these jumpers. So, let me not get into details of that, and it is very easy to follow. The manual contains step by step procedure for all this, and then drag and drop one or more .bit files, and for the type of Vertex FPGA on your XSV board into the FPGA CPLD area, which is this, and of the GX load window. Clicking your mouse on a file name will highlight the name and select the file for downloading. That is by clicking this it will highlight, and this will be energized. Only one bit stream file at a time can be selected. Clicking on the load button causes the highlighted Vertex configuration bit stream to pass through the parallel port and CPLD and then into the FPGA. So, double clicking the highlighted file, we deselect. If you do not want, you can double click. So, just ignore that. It disables the load button if you do not want. So, once you have clicked the load, downloading actually starts. You can have non-volatile storage, and we will not go into the details of this. 2 megabyte flash RAM is available, as I have said, and we will skip all this and go to a relevant portion regarding the IOs that we have already seen. So, these are all basically the same thing. So, all flash RAM, everything, the manual has all this interconnection, and you can see the SRAM there, and the pin configuration, everything is seen here, and video decoder. So, we will skip all this, we are not going into details of this. Here we have expansion header which we have already talked about, and we are going to use this one in order to connect to our extra IO card, which will be dealing next, and after this FPGA card is shown, and that will be used in our first application, namely the traffic controller. And for this we need both this expansion cables connected and on to this expansion header, and so we also next what we will do is we will go on to push button switches, etc., which is here. For example, this CPLD as well as FPGA are connected to the push button switches in this fashion. The DIP switch we have already seen is 8 bits actually, and a single switch, and they are all pulled high here, as you can see. This is VCC or plus 5 volt, and all these signals are going not only to the FPGA but also to the CPLD. So, you can use for even user application can be residing in CPLD, or if not FPGA if the application is much longer in size. And you also have 4 push button switches, and they are also connected in similar fashion. It is normally open, so and they are all pulled to ground. So, whenever you short, this particular IO pin will go low, and otherwise it will be pulled high, that is logic 1. And we have also a bar graph here for that is a LED 7 segment LEDs as well as a bar graph here. Once again they are connected to the CPLD as well as FPGA, and they are all in parallel, so that for depending upon your application you can use either CPLD or FPGA and download your bit stream, and we will be using this FPGA, but we will not be using this LEDs for our traffic light controller, but another IO card which we will be covering next. And some of these LED connections are all shown here, and the vertex FPGA pin actual pin numbers are all shown here. There are 2 LEDs, one is left, other is right, so they go under SL 0 through 6 for 7 segment, and there is no decimal point. So this is rather handicap where a decimal point is required, and in the IO card that we will be showing later on, that decimal point is also available, and similarly a bar graph pin connections are available here, right here. This should be sufficient in order to tackle this FPGA board, and in the next class we will be seeing how this IO card looks like, and we will go into the details, and finally show a demo using this FPGA card as well as IO card, the traffic controller which we have designed before.